Have you ever wondered why one coronavirus popped up in 2003 and then virtually disappeared in just a matter of months, while a closely related one completely changed the world in 2019? Welcome to this explainer, where we're going to dive deep into a massive biological mystery. By examining COVID-19 through the lens of its predecessor, SARS CoV-1, we'll uncover exactly how tiny, microscopic structural differences literally dictate how a virus spreads across the entire globe.
Here's a quick roadmap for today's explainer. First, two viruses, very different destinies. Second, context, the origin of the coronavirus. Third, pathogenesis, the furin cleavage site. Fourth, the transmission paradox. And finally, number 5, prevention and health strategies.
So, Section 1. Dos virus destinos muy diferentes. Let's kick things off with the grand paradox of these two outbreaks.
Look at the sheer scale of this. The COVID-19 pandemic, caused by the SARS CoV-2 virus, reached nearly every corner of the map. It's undeniably the defining public health crisis of our modern era, shutting down economies, overwhelming medical systems, and really just altering daily life for billions of us. But here's the thing. It wasn't the first time a severe coronavirus threatened humanity.
The contrast between these two trajectories is just wild. SARS CoV-1 emerged in 2003. And while it caused a severe respiratory syndrome with a staggering 30% mortality rate in some regions, it was entirely contained within 9 months. Through rapid global cooperation, public health officials successfully hunted the virus down. In fact, there hasn't been a single human case reported since 2004. SARS CoV-2, on the other hand, triggered a multi-year global pandemic resulting in millions of deaths and widespread structural change. So how could two viruses from the exact same family end up with such completely different destinies?
Moving to Section 2, Contexto, el origen del coronavirus. To figure out their different fates, we first need to look at what they actually have in common.
Both of these viruses share a nearly identical genetic toolkit. They're both classified as beta coronaviruses and both originated in bats before making a zoonotic spillover into human populations, most likely through an intermediate animal host like civet cats or raccoon dogs. Now, what makes coronaviruses uniquely dangerous is their size. They have the largest genomes among all known RNA viruses, ranging from 26 to 32 kilobases. You can think of this massive genome like a really complex instruction manual. This large, single-stranded RNA lets them carry more genetic information, creating sophisticated machinery that can tolerate some pretty significant genetic mutations over time. Structurally, they both rely on 4 primary proteins to build their viral bodies. That includes the famous spike protein that gives them their characteristic crown-like appearance under a microscope. But, as we'll see, that crown isn't just for show. It's a highly specialized tool.
Section 3. Pathogenesis. Alcedo the forina. If they're so similar, what exactly is the secret weapon of COVID-19? Let's zoom all the way in to the molecular level.
It all starts right here, with the ACE2 receptor. You can think of the ACE2 receptor as the lock on the front door to your respiratory cells, especially those delicate cells deep inside your lungs. Both SARS-CoV-1 and SARS-CoV-2 have the exact same goal. They desperately want to pick this specific lock. And the spike protein on the outer envelope of the virus? Well, that acts as the key.
Here's the actual step-by-step molecular break-in process. First, the spike protein binds to that ACE2 receptor. But simply grabbing onto the door handle isn't enough, right? The virus actually has to fuse its own membrane with the host cell to dump its genetic code inside. To make that happen, the spike protein has to be cut or cleaved by our own host enzymes. It's kind of like a spring-loaded mechanism that needs to be triggered. Both viruses ultimately rely on an enzyme called TMPRSS2 to trigger that final membrane fusion at step 3. But SARS-CoV-2 has a distinct and frankly devastating advantage at step 2. Let's look at exactly how it bypasses this bottleneck.
The critical difference really comes down to just 4 tiny amino acids. At the boundary of the spike protein subunits, SARS-CoV-2 possesses a genetic insertion known as PRRA. This creates what scientists call a furin cleavage site, and this specific site is totally absent in the 2003 SARS virus. Because of this tiny little insert, our own cellular furin enzymes can actually pre-prime or pre-cleave the spike protein while the virus is still being assembled inside a previously infected cell. So when the virus bursts out and finds a new cell, the key is already pre-cut. The spring is already loaded. This bypasses a major bottleneck, making SARS-CoV-2 exceptionally fast and incredibly efficient at infecting the upper respiratory tract.
Section 4. La paradoja de la transmisión. Let's zoom back out to the population level to see how that microscopic structural change causes massive epidemiological chaos.
This timeline is the absolute aha moment of this whole explainer. check out the divergence here. Back in 2003 with SARS-CoV-1, a person's viral load peaked 7 to 10 days after the onset of their clinical symptoms, meaning people were virtually non-infectious during their incubation period. They only really spread the virus when they were already severely ill, coughing violently, and highly feverish, and by that point, they were likely already isolated in a hospital bed. But look at SARS-CoV-2. Its infectivity actually peaks 24 to 48 hours before you even know you're infected, or right at the exact moment symptoms begin. The virus is replicating at massive speeds in your upper airway while you still feel perfectly fine, walking around, going to work, and socializing.
Think about what that means for public health. An infected individual can unknowingly transmit the virus to multiple contacts before ever realizing they're sick. This renders classic syndromic screening highly ineffective. During the 2003 outbreak, thermal cameras checking for fevers at airports and borders worked incredibly well to stop the spread. You simply found the people with high temperatures, isolated them, and boom, the chain was broken. But because of this pre-symptomatic spread with COVID-19, that thermal screening was completely useless. I mean, you can't screen for a fever if the person transmitting the virus doesn't even have one yet.
Which brings us to a really critical number, 3.28. That's the estimated average basic reproductive number, or R0, for SARS-CoV-2 early in the pandemic. It means one infected person, on average, easily infects over 3 others. Because SARS-CoV-2 replicates so efficiently in the upper respiratory tract, again, thanks to that pre-cut furin cleavage site we talked about, it spreads heavily through fine bioaerosols. These are microscopic droplets that hang in the air like invisible smoke. Just doing everyday, mundane activities, breathing, speaking, or singing in indoor, poorly ventilated spaces quickly turns into a superspreader event.
Section 5. Estrategias de prevención y salud. So, the really crucial question here is, how do public health systems fight a highly contagious virus that you literally cannot see coming?
A virus that spreads silently requires a complete paradigm shift. In 2003, containment and elimination worked perfectly. We identified the sick, isolated them, and the chain of transmission was severed. But for COVID-19, the strategy had to shift dramatically to mitigation and suppression. Because silent pools of pre-symptomatic individuals were constantly bypassing standard case isolation, public health officials had to rely on broad, population-wide actions. This meant rolling out non-pharmaceutical interventions, or NPIs, like targeted lockdowns, and eventually deploying mass vaccination campaigns globally just to slow the spread and prevent hospitals from totally collapsing.
These interventions essentially form a layered suit of armor, what's often called the Swiss cheese model, that's required to combat airborne spread. No single intervention is perfect, but together they build a formidable defense. Because the virus lingers in the air, environmental engineering controls like high air exchange rates and HEPA filtration are absolutely vital for cleaning our indoor spaces. When community transmission levels are high, throwing on a high-quality N95 or FFP2 mask blocks those fine bioaerosols right at the source. And of course, staying up to date with immunizations provides critical internal armor, helping to protect us against severe illness and death, even as the virus continues to inevitably mutate and evolve.
I want to leave you with this thought to consider. If an insertion of just 4 microscopic amino acids can completely alter a virus's transmission kinetics and shut down the entire globe, we have to remain vigilant. We've seen exactly how quickly a pathogen can adapt to exploit our cellular machinery. So the real question is, as viral mutations continue to evolve, are our global immune defenses and public health frameworks truly prepared for the next zoonotic spillover?